Okay, I'm ready to resume. This is where we left off. We're building towards the derivation of the cable equation, which is the fundamental equation that Will Rall worked with to understand neuronal signal processing. And we're doing it by representing a cable, decomposing a cable into a small number of compartments, and this is one of those compartments. And we're going to string them all together to represent a long dendritic cable. And we're going after a partial differential equation that describes how voltage varies along this cable in space and time in response to an input. So here we're thinking about one of these little compartments that we're breaking this long cable into. And I think we worked through how to calculate the axial resistance that's associated with just one of these compartments, and that was here. And I made a big deal of going through the units and make sure they work out. And so let's continue that and derive an equation for the total conductance that's associated with this membrane patch, and the total capacitance associated with this membrane patch. So the conductance of this patch of membrane, the degree to which it permits charge to move out into the outside world from the inside world across the membrane, is proportional to the surface area of that membrane times the density of the ion channels that are in there. And the density of the ion channels in there is given by that specific membrane conductance term that we spoke about earlier. And this is just the surface area of that membrane patch. So if the patch is delta x long and 2r in diameter, that's the surface area of the membrane. And so if we multiply that surface area, which is going to be in units of centimeters squared, times the conductance of that membrane, which will be in units of Siemens per square centimeter, we'll get a value that's in Siemens. That's the units of conductance. So that works out. And the similar logic holds for membrane capacitance. The capacitance of that membrane is determined by the product of its surface area and the specific membrane capacitance. So in this case, it's centimeters squared times microfarad per square centimeter. So we get microfarads for this unit. It all works out. So we can compute the axial resistance conductance, the transmembrane conductance, the membrane capacitance for this little cable chunk using these formulas. And my point was that the units that I presented previously for these quantities therefore make sense and work out in these calculations. So now we're going to do something with it. We're going to build up this cable, this dendritic cable, by concatenating together a bunch of these little compartments. And we're going to represent current flow along the structure using the following electrical circuit. So we're thinking of this part of the circuit as representing the inside world, and this part of the circuit is the outside world, and there are no resistors here, okay? So we're assuming that there can be current flow in the outside, current flowing into the outside world. But potential is the same everywhere. And so there's no resistors here like there are in the inside world. And so there's no voltage drops anywhere. Voltage is the same everywhere along the outside of this cable. And we're going to take it as being ground. It will be our reference point, our reference voltage against which we measure all other voltages. And in particular, the voltage inside the cable. And so we're thinking of each of these nodes. Let's call this node I-1, node I plus 1. They're represented here. So this voltage is the voltage within this little tiny compartment. It's assumed small enough that the voltage variations in it aren't, with space that is, aren't appreciable. So essentially voltage is the same everywhere here. V sub I is the voltage in this compartment. It's taken to be the same everywhere in that compartment, and so on. So this is an axial current. I sub I minus 1 is the voltage, the current rather, flowing into this node, into this face of this cable. there is some resistance to current flow through this structure that's represented by this resistor here. And the value of that resistor is calculated in how I just showed you in the last slide. You had an equation for G sub I. Invert that, that's the value of this resistor. All right? Current that flows in here, a part of it can flow out of that compartment. Some of it is going to flow out through the membrane. And so that current that flows out through the membrane has two components to it. Some of that current can flow through the capacitive nature of that membrane. And so the value of this capacitor is the number that we calculated in the last slide. It's equal to the surface area of this little cylinder times the specific membrane capacitance of a bilayer lipid membrane. And this resistor represents linear ohmic ion channels in the dendritic membrane. Current can flow out of the core conductor through that membrane resistance. The value of that resistor is set by the formula from the last slide. So we know how to calculate this resistance, this capacitance, and this resistance, all using equations from the last slide. Let's assume that all of these delta x's are the same, and so we've got the following electrical circuit representation of this structure. Are we good with that? That's pretty clear, I think. Yeah.
So the places where the current's going from inside to outside is in between the cable compartments?
These currents here represent the ability of charge to leave the circuit through this membrane, the membrane of that compartment. And so there are two such currents. One is capacitive. So if voltage is changing, there will be a capacitive current, and there will be a resistive current that are through the assumed to be ohmic ion channels that are populating that membrane. This current here is current directed along the axial resistance of this compartment. It's axial current. This resistor is the resistance to current flow along the length of that little compartment. So this stuff here is that compartment. This stuff here is that compartment. And we're hooking them all up together. Okay, we do this so that we can derive the cable equation, and it goes like so. So we can write an expression for the voltage in this compartment at this node, V sub I. And so this voltage is equal to whatever this voltage is, V of I minus 1, minus the voltage drop across this resistance. And so that voltage drop is just the current flowing through that resistor times the resistor value. So this is the equation we derived in the last slide. And this is the current, whatever it is, through that resistor. So this voltage here is equal to this voltage minus this voltage drop. So delta VI, which we define as the difference between voltage at node I and node I minus 1, is just the negative of the voltage drop across this resistor. This is just elementary circuit theory. And so remember that this formula for this resistor is dependent on the incremental length delta x. That's why that delta x term is here. We're using it to calculate surface area of that membrane. So if we divide both sides by the delta xi, we've got a delta v over a delta xi, and we let delta x get small. We're partitioning this cable into smaller and smaller compartments. We'll get an expression for the partial derivative of voltage with respect to space. And it's just this term. It's just straightforward algebra. And so we have now an expression for the axial current at some location. It's equal to this stuff times the spatial gradient of voltage. Now that makes intuitive sense. The spatial gradient of voltage is the driving force, if you will, in the axial direction along the cables, and that's just the resistance value. So this current is this is a conductance value, actually. And so this current is just equal to a conductance times a voltage difference. It makes intuitive sense. So we're going to return to this equation later on, so we'll label it as equation 1 so we can come back to it. And so we've worked out an equation in voltage, involves dV dx, for the axial current, and now we're going to go after similar equations for the transmembrane voltages. And so we know from Kirchhoff's current law, you used to have to take circuits, right? You don't have to take it anymore. But we would have beaten you to death with Kirchhoff's current law in your course on circuits. And so, of course, Kirchhoff's current law is just saying that you pick a node in an electrical circuit and you look at the sum of all of the currents entering and leaving that node. They must sum to 0 for all time. Because at any given instant of time, there can be no charge accumulation at a node. What goes in has to leave. It's just a conservation law. And so Kirchhoff's current law says that the current entering this node is equal to the currents leaving that node. And so the currents leave this node in 3 ways. There's a resistive transmembrane current, there's a capacitive transmembrane current, so here they are. And then there's the axial current exiting that node. That's this current here. And so again, we'll define a delta I, a change, a small incremental change in the axial current. It's just the difference between the current at node I plus 1 minus the current at node I. Okay? And so that difference, if we subtract from I plus 1 the value of I sub I, just rearranging terms here, we're going to get the negative of the resistive membrane current and the capacitive currents. And these are those currents. Right, so you know where this expression came from. The current through a capacitor is just the time derivative of the voltage across the capacitor times the capacitor value, right? That's the current through a capacitor. This is the current through that resistor from Ohm's law. So that's delta I. Does that make sense to everybody? Okay. So we're going to play the same game. We've got an expression for delta I sub I. We're going to divide both sides by delta x and take the limit as delta x gets small, and we're going to get a partial derivative of the axial current with respect to space, and it's this expression here. So it's clear where it came from. It's we're losing axial current, if you will, by current that flows through the membrane, and that's what these two terms represent. So that's our second equation. So I'm just bringing equation 2 over here. And at equation 2, we've got the spatial rate of change of axial current. What we're going after is a single equation for how things are changing in the circuit that's expressed in voltage. We don't want 2 state variables. We want to work with 1 state variable so we have a chance of solving an equation in that 1 state variable. So we've already derived an equation for axial current. That was equation number 1 a couple of slides back. So here's the repeat of that equation. And so now to get rid of current on this side, all I need to do is take the partial of this with respect to x. And I've got that term. And so now on the left-hand side of this equation, I'll have an expression that is completely in terms of voltage. And it's this here, right? And so just bring this stuff down. There it is. So the axial current is the second derivative of the voltage of that node with respect to x. And so you're with me on this. It's just a simple substitution. And then if we just fool around with the algebra, we ultimately get to the final form of an equation for the state variable, which is voltage at some location along the cable, which is, and we only have voltage as a state variable here, and it's a second order differential equation. This is what is known as the cable equation. So it involves these parameters, this parameter. So this has a special property. This parameter has a special property. We'll derive that in a minute. And this is the cable equation. It's a second order constant coefficient ordinary differential equation, linear. And we know how to solve such equations. We can write down the solutions. So ultimately here, now that we've got the cable equation, at least in the steady state, we can very simply solve for voltage in the steady state. And we'll go through that solution in just a minute. But now I want to talk about the physical meanings of these two terms that emerged in our cable equation. So let's take our cable and imagine that we have the same capabilities of Hodgkin and Huxley, who, as you know, chose to work with the giant squid axon because it's big. And you can run a wire down the middle of that axon, and you can inject charge everywhere along that axon and clamp a long piece of biological membrane, a cable, a dendritic cable of sorts, to a single voltage value. It's called space clamp. So we're going to imagine that we impose a space clamp on our cable. So now voltage doesn't vary in space anymore. It's locked everywhere along the cable at some value V sub 0. So this side of the cable equation, that's 0. And we're left with these terms. And we're left with this initial condition, voltage everywhere along the cable for any x at time 0, that's the initial condition, is V0. Well, so this is just a first order linear constant coefficient differential equation. We know the solution for this equation. We can write it down. And it's this, right? So at any x and any t, the voltage, if we impose that voltage at time 0, set voltage everywhere at time 0 along the cable, and then then shut off all of the charge that is needed to maintain that voltage. The picture you should have in your mind is that initial charge to set every location of that giant squid axon to voltage V0. We've been injecting charge everywhere, charging up the membrane capacitance. So when we turn off that current, everywhere along the membrane, it's sitting at voltage V0. So at time 0, we shut that charge off, and then charge begins to dissipate, right? So the key question here is, create this mental picture. You've got this cable that has some length. Every point along that membrane has been charged up to some voltage. When you stop applying current, once that charge is there, you release the current, charge will begin to flow. Where does it flow? What's the nature of that flow? Where does charge go? How does the membrane capacitance discharge? Let me start by asking you, is there any axial current flow in that system? No, I see his head shaking no, and that's absolutely right. There's no voltage gradient in that system. There's no voltage gradient. There's not going to be any flow of charge along the axial direction. So what we know from that is that however membrane potential changes, it's going to change uniformly everywhere in space. Every point in space is going to do the same thing at the same time. Where does charge flow? How does the capacitor discharge? There's only one pathway by which that capacitor can discharge. What is it? Say it again, please. Radially? What does radial mean here? Going to the outside. It's that charge it'll discharge off the capacitor through the membrane resistance. And so it's going to leak out through the membrane resistance everywhere along the cable at the same rate. And we know that that rate is this thing here. It's the product of R times C. It's the membrane time constant. A parallel RC circuit charges and discharges with a time constant that is the product of R times C. So that's what this term is. It's known as the membrane time constant. We're going to call it tau. Remember I said in the last lecture that we're going to think of normalized space and normalized time when thinking about dendritic signal processing and these cable equations. We've just got our first time normalization factor. This becomes an inherent property of the cable that we're thinking about. It's determined by the bilayer lipid membrane intrinsic capacitance, and it's determined by the intrinsic resistivity of that membrane. And once those are set, we have a natural time constant in the system by which we can normalize time. So what we're going to do is we're going to express time, we're going to call lowercase t, which is time, absolute time. We're going to call it capital T, which is normalized time. And capital T is equal lowercase t, absolute time, divided by the time constant. So we're expressing time in units of time constant. That's why this is important. All right, now let's figure out the intuition into this term here. Again, capital R sub m and R sub I, these are the specific membrane resistance, the specific axial conductance of the membrane. These two parameters and C, we need to know these for any neuron that we're studying. And so the way you get them is to guess at their values. Well, you can measure their values, and we're not going to talk about that. But from doing many experiments, we can accumulate a body of knowledge about how these R's vary, and there's very little variation in C. And so they become a property of the particular kind of neuron that we're studying. And so we're going to take a similar tack in understanding what this coefficient means. And the mental picture I now want you to create is imagine that you have a dendritic cable that is so long that we're going to consider it to be infinite in extent. And at some point in that cable, we're going to inject a current, and we're going to watch how charge distributes along the cable. And we're going to maintain that current for a long time. And so initially, charge will flow in the cable, the membrane capacitors will become charged, will charge up, but things will settle down over time, and every point along the cable will take on a particular there will be a particular voltage at every point along this cable. And that will be a steady state voltage. How do you think that voltage changes as you move away from the site of current injection? What happens to voltage? You're looking at the steady state voltage profile along this infinite cable. How does it change? It's at a maximum where we inject current. How does it change when we move away from that location? It's dropping. The voltage decays in a more complex way than being inversely proportional. It's still simple. The voltage decays exponentially. So just like the voltage, when we set the cable to have a uniform initial voltage, things changed in time at an exponential rate. When we have an infinite cable and we're injecting current at one place, in steady state, the voltage profile will fall exponentially away from the site of current injection. And we can prove it because if we consider the steady state, then dV/dt is by definition zero. Voltage isn't changing anymore in time, it's zero. That's what steady state means. And so this cable equation reduces to this equation, which is now a constant coefficient second order differential equation. We know its solution as well. It's this. And we can prove that the spatial rate of decay is given by this term lambda, which is defined as follows. It's just the square root of that term out here. So we're calling this thing the space constant. And it tells us how rapidly voltage is decaying along a cable as we move away from the site of current injection. So let's do the mental exercise of asking the question, suppose membrane resistance is increased, membrane conductance is decreased, right? So what happens to the space constant when we put fewer ion channels in the cell membrane through which current can leak to the outside world? How does that change the space constant? Obviously, the space constant gets bigger. But the reason for that is if I'm sitting at a point in the cable and I'm current, I got two directions I can go. I can flow axially or I can flow out of the membrane. If the resistance of the membrane is now higher, I'm going to choose to flow axially. So that current will travel further along the cable, charging up membrane capacitance to larger values. And so the space constant associated with the cable is larger. The effect of that current injected at one location is spreading out further than it would have otherwise. And in just the same way, if we increase the axial resistance, right? Play the same game. I'm current. I'm at a point in a cable. I can flow this way along the cable or this way out through the membrane. If the axial resistance goes up, I'm going to tend to flow out through the membrane. So more charge is lost. The spatial extent of the spread of voltage away from the site of current injection will decay more quickly. The cable is shorter, right? So this is the physical, intuitive meaning of space constant. And now it becomes a natural distance, a natural number, I should say, in which to express distance. So we'll now define a quantity electrotonic length. We already talked about time and normalizing time to be expressed in units of the membrane time constants. We're now going to express space in units of the space constant. So whatever the physical length of a piece of membrane is, you give me Rm, Ri, Cm, I can calculate in the diameters of that cable, I can calculate the space constant, and I'm going to express its length in this dimensionless variable we'll call capital X. That's its electrotonic length. Length in units of space constant. And when we make these variable substitutions, the cable equation takes on a really simple form. It's just this. All the parameters go away. Yes, bravo, yes. I didn't do it, Rawl did it. And so it's very simple. Okay. Now we want to harness this cable equation to do something useful. And so real neurons don't have dendrites that are infinite in extent. They can be long, but so actually, let me say that the fundamental Rawls versus Eccles argument, therefore, was what is the electrotonic length of dendrites, right? That's the fundamental question that they were fighting over. Eccles said he didn't express it this way, but what he really meant to say was the electrotonic length of real neuronal dendrites is so large that at the distant portions of dendrites we're many space constants away from the cell body. Therefore, this voltage profile that's decaying at an exponential rate away from the site of synaptic input or current injection, that profile is decayed so much by the time we get to the soma that synaptic input won't have much influence on neuronal firing. And Rawls was really saying, the electrotonic length of dendrites can be fairly short. And guess what? Even though they can be physically long, their electrotonic length tends to be fairly short, which means distant inputs can have an influence on soma. So what we're now going to do is examine the properties of cables that aren't infinite in extent but have some finite length. And remember, length is now going to be expressed in the dimensionless variable capital L. We can imagine a current flowing into this cable on one side at x equals 0, so I'll call that current I sub 0, and that voltage there that is produced there, V sub 0, and there may be a current flowing out of the end of that cable. Depends on whether the terminating conductance of that cable is 0 or not, right? If there's 0 output conductance, there's no current flowing out, but there will be some current at that location and some voltage at that location. G in is the input conductance, G out is the output conductance. And we can solve for voltage everywhere along this finite length cable. And we're going to do it in the steady state. And I don't think I want to go through the entire solution. I want to frame it for you and show you where we get to. So the general form of the solution is shown here. C1, some constant C1 times e to the x, where x is normalized spatial location, plus C2 e to the negative x. So if you plug that into the cable equation, that is a steady state solution. We're only talking about things in the steady state here now. That's why I've dropped time, because these solutions are only easy in the steady state. You can do them, you can derive the solutions for transient responses. It's just much more difficult. So Will Rall was always full of tricks. He kind of knew where he was going, and so when he wrote his papers, he leveraged what he'd labored for hours to figure out, and he knew where he was going, and so he'd introduce a mathematical trick, and you scratch your head and you wonder, why in the world would you do that? Well, he knows where he's going. He knows it's of advantage to do the mathematical trick. So the first mathematical trick he used was to define these constants A and B and rewrite C1 and C2 in terms of A and B and E raised to the power either negative L or E raised to the power L, where L is the distance of that cable. So this is just a number, and this is just a number, and you can always pick A's and B's that do this. You can derive what they are in terms of C1 and C2. So you can always rewrite the solution like so. Okay. And where Rall wanted to go was into what he considered to be the simpler world of representing these solutions as hyperbolic cosines and sine functions. And so that's really why he introduced the A and the B here, because if you multiply out and isolate terms, this equation has the following representation. And this is just the hyperbolic cosine of L minus x. And this term is just, well, I should say with the divided by 2, is the hyperbolic sine of L minus x. So this is just massaging the form of the solution. So the form of the solution, it can always be written in this manner, yeah.
Shouldn't the second term have
A minus sign between the two exponentials. Oh, probably. I think I always screw that up. I always get these sinh and cosh's definitions wrong.
No, just because they're the same and
Yeah. You're right. You're absolutely right. Sorry. Thanks for that. You think I'd learn. I don't. Okay. Now, I don't know that I want to walk you through the solution. You can do it yourselves. The whole reason for going through this derivation is that there came out of this a great form. So Rall was going after the equation for the input conductance of this finite length cable. And so to get that input conductance, we need to know the relationship between input current and input voltage. And so just intuitively, we already have an equation for axial current, and so we leverage that equation. And we leverage the solution form that we developed in the last slide to get expressions for I of 0 and V of 0, and they're in these terms of these unknown parameters A and B. And so when we divide one by the other, that all boils down to this. And you see that the input conductance is equal to our intrinsic cable parameters times the ratio of B over A. And so what is so elegant here is that Rawl showed what B over A is in terms of the intrinsic cable properties. It's a very nice solution. So I'm sorry, I'm not going to go through that, just to save us some time here, because I like to tell stories more than give lectures, so I tend to go slowly in lectures. And so you can work that through. And so to figure, yeah.
In general, when using cable theory to model the neuron, are we accounting for the active effects of the cell? Because surely there's more than just length and time as you're moving along with the neuron that affects current. Probably there's voltage-gated channels that then spike current at later points. Those active effects.
Yeah. Great question. I think at some point in Monday's lecture, I said that Rawl cable theory is actually wrong, right? It doesn't incorporate our fully modern understanding of neurons. And our modern understanding of neurons is that there's really no such thing as a linear ohmic ion channel. They're all voltage gated. They're all highly nonlinear. We know that they are placed into dendrites because they've been labeled fluorescently and imaged in dendrites. So we know that's a violation of some of the assumptions that Rawl has made. We know that there are pumps and transporters that are driven by voltage, that are driven by ion gradients. They're in dendrites too. They're sources of current flow through the membrane. We know that there's signal transduction mechanisms occurring in the dendrites that are modulating, dynamically adjusting the properties of all transporters. These are all violations of Rawl cable theory. And so fundamentally, you're right. There are other things going on that are very important. And what I find remarkable here is the idea that a modeling approach that we can easily tear apart nowadays, we know it's wrong from first principles, yet it's so simple, makes so few assumptions, and doesn't have these complexities, yet we still learn a lot from it. And the fundamental thing we learn a lot from it about is, are neuronal dendrites really compact or are they really big? Can there be distinct regions of a dendritic tree that are in electrical contact with one another, but not with the soma and not with other regions of the dendritic tree? Can distant inputs really influence what this neuron is doing? This theory really laid the basis for everything that's been built since on our understanding of how neuronal dendritic trees process information, even though it's wrong in many ways. And I like that. I think it's pretty cool that in some way Rawl got to the real essence of the problem. Yeah, there were these other things going on and we know they're important, but he answered the essence of the question about the nature of dendritic signal processing as opposed to the Eccles view that only these inputs landing near the soma can really do anything. So I think it's important for that reason. And so how do we overcome these challenges that you're talking about? Well, the way we overcome it is the basis of the next lecture, which is on compartmental modeling. We actually go in and break apart and represent each of these little subunits that we use to motivate the cable equation and from which we derive the cable equation. Well, now in a compartmental model, we'll actually consider them as the building blocks from which we compose units. And if we're going to solve, and from that process, we won't get a partial differential equation that represents a dendritic tree. We'll get a system of ordinary differential equations. And we can make them as complex as we want. So if we want to stick in voltage-gated ion channels, or we want to stick in energy-requiring pumps, in they go into each compartment. And we're going to solve the equations on computer anyway, so who cares, really, how complex they get, as long as they're really driven by the underlying biology. So that's how it's now dealt with in today's world, that we directly simulate the small details of the structure of the neuron. We incorporate the biophysics that are really there. But you'll see in a minute, if I ever get to the end of this lecture, that people are still doing this kind of analyses in the brain. I'm going to show you a paper published in 2017 that uses these simple ideas to show us something important about types of cortical parameters. So, you know, it's still a fundamental contribution, despite all of the complexities that you have raised. All right. What Will-Rall proved was the ratio B over A. It's equal to the output conductance divided by the input conductance of the semi-infinite version of that cable. We defined this in the first lecture. We talked at length about that in the first lecture. B over A is just this ratio showing you how fundamentally important these two parameters are. And so we now have an equation for the input conductance of a finite length cable. It's this thing here, and I do want you to know that. And it'd be good to go through this derivation and see how it's done. And so why is that important? If we're going to inject current at one end of the cable, if we know the input conductance, we can compute the voltage at that site on the cable. And if you've already got an expression for voltage anywhere along the cable, then if we divide by the voltage at the starting point of the cable, we can derive an expression for how voltage decays along the cable at any location x relative to point 0, and it's this formula here. So this was buried in another derivation in a slide that I really skipped over, and I just showed you the solution. But voltage at some location x in response to a current injected at one end of the cable is equal to the voltage produced at the site of current injection times this stuff. And there's only a handful of parameters. They are G out, G infinity, and the electrotonic length of the cable. With those three things, and they're all in turn computed from knowing the diameter of the cable, specific membrane capacitance, specific membrane resistance, axial resistance. So you can get voltage anywhere along a cable armed with this information. And that's fundamentally what Rall proved. And so I'm taking you back to a picture that I talked a lot about in the first lecture. We didn't derive this stuff, but I told you how the results that Will-Rall obtained allow you to understand how a synaptic current injected at anywhere in a dendritic tree, you could calculate in the steady state the distribution that that input produces anywhere within this dendritic tree. And I walked you intuitively through that picture of how we do that. And the picture of how we do that is we leverage the expression for the input conductance that I just walked you through. It was that expression here. So if we're injecting current at this node, the voltage at the point of current injection is equal to the current that we are injecting divided by the input conductance looking into the tree at that point. We know what this input conductance is into that part of the cable. It's given by this formula here. The thing is, we've got to deal with these G outs. And I talked a lot about that in the first lecture, right? The terminating conductance is the conductance looking into this cable and the conductance looking into the rest of this dendritic structure. So there's an iterative way to figure that out, but we can get it, and once we've got that input conductance here, we can compute V0, and then we can compute voltage anywhere along that cable. And we just keep doing this over and over and over again. Yeah, that's telling me it's time to stop almost. So here's a picture of injecting a current into this point in this artificial dendritic tree. And what we're showing you here is how voltage decays away from the site of current injection. It's very high at the point of current injection, and it's decaying as we progress to these various points closer and closer to the soma. And so it's decayed by a factor of 3 or so by the time it gets to the soma. So that, yes, there is attenuation, but suppose we applied a current like this here, another one like that here, 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 here. Well, they're pretty much going to add up to one another. Their effects are pretty much going to add at the soma. So if we had a bunch of even distant synaptic inputs on this neuron, its influence at the soma is going to be 2, 3, 4, 5, 6, 7, maybe 8 times the influence of just one input. And so even a somewhat small influence due to synaptic input at one location, if that's multiplied at many locations, that can integrate and add up and influence the way in which this neuron fires. And before we go, I want to take you to this real diagram. So here's the paper. Comprehensive morphoelectronic analysis shows 2 distinct classes of L2 and L3 pyramidal neurons in human temporal cortex. So here they are. They looked at 60 cells. You can see what's happening. These projections, these dendrites are getting larger and longer. The cells are getting longer and longer and bigger and bigger. So these guys picked up on that. Okay, we see that the cell diameter is, the cell extent, the dendritic tree extent is getting bigger and bigger in different locations in temporal cortex. What does that mean? So what do? Here they plot the physical length of these dendrites for cells at 2 different locations within temporal cortex. And so they find a population of cells that have shorter dendrites, a population that tend to have longer dendrites, and they computed the length of the equivalent dendritic cylinder representing those dendritic trees. They essentially built a cylinder model, a single cylinder model of the dendrites, and they asked the question, what's the electrotonic length of that cylinder? Well, for these, it's, maybe, who knows what it is on average, maybe about 0.6 or so. For these, it's maybe 0.9 or something like that. And so you see that physical length does also correspond to slightly greater electrotonic length. But the electrotonic lengths of even these large dendrites are less than 1. What does an electrotonic length of 1 means? If voltage is decaying exponentially away from the site of current injection, and the rate at which that happens is the space constant, that means that 1 space constant away from the site of current injection, voltage is attenuated by about 70%, by a factor of 1 over E. And so the fact that these dendrites, even though they can be big, well, or even these, they're on average maybe 0.8 space constant. That means the attenuation from the very tip to the soma it's not going to be 70%. It's going to be 50 or 60% or something like that. So even in these big, even in these big neurons, these long ones, distant inputs are fairly close in electrical terms, in units of space constants, to the soma. And so this shows you, this paper is written in 2017. So we know these pyramidal cells have active channels in their membrane and transporters and signal transduction events and channel phosphorylation and inputs land on spines, not right on the dendrites, and so on and so forth. But yet here's an example of a great group, Idan Segev's group, doing the kind of Raleian analysis that we spent these 2 lectures talking about. So you see how it still factors importantly in the thinking of modern day neuroscientists. They care about what the electrotonic dimensions are of this long dendrite, and it means something intuitively. It tells them something intuitively about the signal processing done by those cells. So I would like for you to go through those derivations. They're just algebra. So go through them and see where things come from And know the formulas that were on the first 2 slides of this lecture. I said that's what you got to know. I don't lie. That's what you got to know. You won't be asked anything else. That's it. Those 2 slides, those formulas. Thanks.